quickly introduce myself. My name is Anand Narayanan. I teach and I do research in astrophysics at the Indian Institute of Space Science and Technology, which is a deemed university under the Department of Space, Government of India, here in Trivandrum. And so that's where I have been for the last 10 years. We have a postgraduate program in astronomy and astrophysics at IIIST, and we also, some of our undergraduate students also take courses in astrophysics. So today's presentation is going to be on a field of astrophysics that has been unfolding for the last 25 to 30 years or so. It's been a field in which tremendous progress has been made in the last 2 to 3 decades, and this is the discovery of planets beyond the confines of the solar system. Okay. So we know that there are planets that are going around the sun, but sun is not the only star in our universe. In our own galaxy, there are roughly 200 billion stars. So a billion is 1 followed by 9 zeros. So there are countless numbers of stars in our own galaxy, Milky Way. So there is no reason why our sun should be in any way special. Okay. So there's no reason why our sun should be the only star hosting planets around it. So for a very long time, people have been speculating on the possible presence of planets around other stars. But actually discovering them, actually detecting them, seeing some observational evidence for the existence of planets around other stars, that has happened only in the last 30 years or so. And so in today's talk, I'm going to take you through very quickly on this particular topic in astrophysics, which is the detection and characterization of extrasolar planets, which are planets orbiting other stars. So before I start my presentation, let me just mention that my internet is connected through my phone. So during the course of this presentation, if I get a phone call, then my connection may be interrupted for a few seconds. So I would request all of you to stay tuned, and I will try to log back in. If my connection gets disrupted, I will try to log back in as quickly as possible. Okay. So with that, let me start sharing my screen. So someone can tell me whether this screen is visible or not. Is it visible? I am not able to.
Yes, sir. Visible.
Yes, sir.
Yes, sir. Yes, sir.
Voice is also okay, right? I hope there is no lag or anything. It's fine.
Everything is perfect, sir.
Yeah, okay, thank you. Thanks for confirming. So why is the discovery of planets around other stars so exciting? Okay. Astronomers want to understand a lot of things about planets, how planets form around stars, how they organize themselves around stars. So that is how diverse can planets be, etc. But from a common person's point of view, the reason why it would be of some interest to a common person, this discovery of extrasolar planet, is because one of the questions that humankind has been dabbling with, has been trying to find an answer for the last several centuries, is whether there is a possibility of life elsewhere in the universe. Outside of Earth, could there be any other world where life, the phenomenon of life, is present? Okay. And first crucial step in and addressing that question is to actually look for life within the solar system. But beyond that, okay, there's no need to confine the search to within the solar system. Beyond that, around other stars also, if there are planets, then that really amplifies the chances of finding a planet with conditions that are favorable for life to exist. Okay. So this is why this field of extrasolar planet studies, the discovery of planets around other stars, has been getting a lot of press publicity also. Whenever extrasolar planets are discovered, and if the planet discovery has something peculiar, then immediately most of the newspapers write about it. There are scientific magazines to talk about it. And the reason why all this PR is happening is also because this discovery of extrasolar planet, as I mentioned, feeds into this larger question of finding life elsewhere in the universe. So let's start this presentation by closer to home by looking at planets of the solar system itself. So for the most part of the history of astronomy, the only direct evidence that scientists had, that astronomers had of planetary system is our own solar system. This was the only example that we had. So if you look at our solar system, we have the sun and we have planets in the inner part of the solar system. These are usually rocky planets. These are very dense but small planets, and they are made of non-volatile materials like iron, aluminum, silicon, etc., which forms rocks. And so these are also called terrestrial planets. And further away from the sun, we have large gaseous planets that are made of gases, okay, hydrogen, helium, methane, ammonia, so on and so forth, and also ices. The core of some of these gaseous planets can have ices. So based on this one example of our solar system, astronomers had an elaborate theory of how planets form around stars and how they organize themselves. The theory is based on the idea that closer to the sun, the amount of heat and radiation would be so high that only hard elements like iron, silicon, etc. can condense to form planets. Material that is volatile, that can be easily vaporized, that can easily become gas, they combine together to form planets much further away from the sun. Okay, so that was the picture of what a planetary system should look like. But if you have ever looked at the night sky, you know that sun is not the only star. There are untold number of stars in the night sky. So here is a picture, here is an astrophotograph of the night sky from the Leh region of Ladakh. In the foreground, what you're looking at, the structure that you're looking at is a telescope called the Himalayan Chandra telescope, which is in Ladakh, and it is owned and operated by the Indian Institute of Astrophysics in Bangalore. So the telescope is not what is important in this picture. What I wanted to show you is that if you go to a dark location and keep looking at the sky, okay, you will find that the sky is sprinkled with infinite number of stars. And all of these stars are like our sun only. Okay, so there is no reason why only sun should have planets around it. In fact, the current understanding is that whenever stars form, planets also form around it. Okay, so planet formation seems to be a natural outcome of star formation. So it's possible that at least a good fraction of the stars that we see in the night sky have planets around it. So then the question is how to find them. If solar system is not the only planetary system in our universe, then how can we go about finding these exoplanets or extrasolar planets? Now, as it turns out, there are some challenges. There are some barriers in directly detecting extrasolar planets. Okay, so one of the challenge in directly seeing extrasolar planets is the fact that planets are incredibly small compared to stars. So if you take our own solar system as an example, I'm sure most of you would have seen this picture. Okay, this was circulated widely through social media several years ago. So this picture is actually to scale, and the big object that you're seeing is our sun, and all the small objects that you're seeing on the right corner, those are all planets of the solar system. Okay, so this picture I'm showing just to remind all of us that the planets are incredibly small compared to a star. For example, Earth is about 1/100th the size of the sun. And Jupiter, which is the most massive, biggest planet in the solar system, it is about 1/10th the size of the sun, which means that you can stack 10 Jupiters from one edge to the other. So that's how big the sun is compared to these planets. Okay? So planets are incredibly small compared to stars. And these stars are at enormously large distances from us. Okay? So the nearest stars are several light years of distance away from us. So just to remind you, light year is the distance that light travels in 1 year. So traveling at a speed of about 300,000 kilometers in 1 second, the amount of the distance that light would cover in 1 year is what a light year is. So it's a very, very large number. And the nearest stars are light years away, and most of the stars that we see in the night sky, they are 100 to 1,000 to tens of thousands of light years away from us. So at those large distances, even a star looks like a point source, okay, to us. And even with the help of a telescope, if you try to look at these distant stars, even through a telescope, stars look like point sources. So planets which are already very small compared to a star, they will be even smaller than a point in the sky. So that's what this animation here shows. So here is a hypothetical star and a planet around it. Assume that this star-planet system is at some 100 or a 500 or 1,000 or 10,000 light years of distance away from us. So sitting here on Earth, when we turn our telescope and try to capture a picture of this star, the star itself will be a point source. So the chances of finding something that is even smaller than a point is right next to that star is very, very small. Okay. And the other fact, so the one is the difference in sizes. The other is the brightness contrast. Okay. Stars are incredibly bright when compared to planets. Just to give you an idea, in visible wavelength region, which is where many of the ground-based telescopes operate, in visible wavelength region, the contrast in brightness between a star and a planet that is going around that star is roughly of the order of 1 to a billion. Okay. So what that means is when we take a telescope and point at a star, and suppose that star has a planet around it, then in every second we may get a billion photons from the star, but we may be getting only 1 photon from the planet. So there's a huge brightness contrast. Okay. So this also makes direct photography of extrasolar planets very difficult. Okay. So when we take pictures of the night sky, the stars will be clearly seen in those photographs, but the planets which are smaller than a point in the sky and sitting very close to a bright star, okay, it will be very difficult to see it. Usually the analogy that people use is, it's like trying to photograph a firefly that is sitting next to a floodlight. ഒരു മിന്നാമിനും ഒരു വലിയ സ്റ്റേഡിയത്തിലെ ഫ്ലഡ് നടത്ത് ഒരു 1000 വാട്ടുള്ള ഫ്ലഡ് നടത്തിരിക്കുകയാണെങ്കിൽ, so when you take a picture of it, your picture will be fully lit up by the light from the floodlight, and you will not be able to see the firefly. So this is something similar to that. Okay. So that doesn't mean that we cannot find planets around other stars. As it turns out, there are some very good indirect ways of establishing the existence of planets around stars. The two most successful indirect methods for finding exoplanets are, one is radial velocity method and the other is transit method. Okay. In the entire history of exoplanet detections, these two techniques have been most successful in finding planets around other stars, and both of them are indirect methods. The reason why they are called indirect methods is because the discovery of the reason why they're called direct method is because the planets are found not by actually seeing the planet, but by looking at a behavior of the star around which the planet is revolving. So we don't see the planet. Instead, the observation is confined to the star. Okay? And by measuring certain properties of the star, astronomers infer the presence of an unseen planet around it. So in both radial velocity method and transit method, we don't directly see the exoplanet, but we come to the conclusion that a star has a planet, one or more planets revolving around it based on some peculiar behavior of that star. So I will tell you what that peculiar behavior is. So in this presentation, we will be spending most of our time trying to understand this radial velocity method and transit method. Okay. So first, let's look into radial velocity method. The underlying principle behind radial velocity method is very easy to understand. Okay, so normally we think of when we think of a star-planet system like our solar system, we normally say that the planets are revolving around the sun. Okay, in the case of our solar system, so which means planets are revolving around stars. And what keeps the planets in their orbit around the stars is the mutual force of gravity between the star and the planet. So there's a force of attraction between the star and the planet, which is the gravitational force. But we know that gravity is a mutual force. The star is going to exert a certain gravitational pull on the planet. The planet in turn is going to exert the same gravitational force on the star. But since stars are much more massive, 1,000 times more massive usually compared to planets, okay, the planets end up going around the star and the star doesn't move much. Okay. But in reality, if you want to give an exact description to this entire scenario, okay, the exact description would be that the planet is not actually going around the star, but the planet is going around the center of mass of the star-planet system. The center of mass is like, I'm sure all of you are familiar with what a seesaw is. So on a seesaw, if two people of equal weight are sitting on both sides of the seesaw, the center of mass will be at the center of the seesaw. If you have a heavier person sitting on one side, the center of mass will be closer to that heavier person. Okay? So in the same way, since stars are much more massive compared to planets, the center of mass is going to be much closer to the star than the planet. In the case of our solar system, if you use our solar system as an example, the case of our solar system, the center of mass between Jupiter and Sun is actually inside the Sun itself. Not at the exact center of the Sun, but closer to the Sun's surface. The center of mass between Sun and Earth system is actually very close to the center of the Sun. So now you can think of a star-planet system where the planet is sufficiently massive and it is close to the star. So the force of gravity, the pull of gravity is more. And as a result, the center of mass can be outside the star. So then what happens is, as the planet revolves around the star will not, around the center of mass, the star will also be going around the center of mass. The planet will be going around the center of mass in big circles, and the star will be going around the center of mass in smaller circles. Okay? And so this is what will be happening in the case of stars with planets around it. So I'll just play a video that shows it. So this is not actual real data. This is just a computer visualization of to explain the scenario. So you can see here hypothetical star and a planet revolving around it. Okay, so the planet is going around the center of mass of the system, and the planet is held in its orbit by the mutual gravitational force between the star and the planet. The star cannot remain stationary. The center of mass is outside the star, so the star also goes around the center of mass. So now let's say that we are astronomers and we are randomly monitoring stars in the sky, and our objective is to find planets around them. So even if we don't see the planet, suppose let's say that our telescope is pointed at stars at random. Okay, so we are looking at this particular star. Our telescope is collecting light from the star, and that the light that the telescope collects is sent to an instrument called a spectrograph. A spectrograph is like the prism that we have all used in school. Okay, the purpose of the spectrograph is to split the light from the star into its component colors, into its component wavelengths. Okay, so that's what a spectrograph does. In physics terms, we say that the spectrograph disperses the light. It splits the light into its component energies. So when you have a telescope and a spectrograph connected to it, and the spectrograph will render a spectrum of that star, it will produce a spectrum of that star, and that spectrum will be captured by a CCD camera. And so the spectrum would look something like what you're seeing at the bottom of it. Okay, if you're looking at visible wavelength region, you'll see the colors of the rainbow going from violet to red, and so that will be the spectrum of that star. But in addition to those colors, those gradient of colors from violet to red, you can also see some black lines. So these black lines, they are absorption lines produced by atoms and ions that are present on the surface of the star. Okay? The star is a huge ball of gas, and on the surface of the star there can be atoms of hydrogen, there can be atoms of sodium, magnesium, calcium, etc. So all these atoms and ions will absorb some of the photons that are coming out from the star, and so those absorption lines will appear as dark lines in the spectrum. Now, these absorption lines are expected to be at some particular energy, okay, at particular wavelength or frequency. And so they are expected to be at a certain wavelength. Okay, but now if the star is not stationary relative to us, if the star is moving around like this, okay, then at some time in its orbit it will be moving towards us, and at some other times it will be moving away from us. So if you have a source that is emitting light, emitting electromagnetic radiation, and if that source is coming towards us, then we know that the light will get blue shifted. It will shift towards higher energies. This is called Doppler effect. And if the source is moving away from us, the light will get red shifted. Okay, that's also Doppler effect. So when we are looking at a star with a planet around it, the star is not stationary. It will be going around in these small circles, and at some time it will be coming towards us, and some other times it will be going away from us. So when we look at the spectrum over long periods of time, we will find that the spectral lines are blue shifting, red shifting, blue shifting, red shifting in a periodic manner. This periodic shift in the spectrum of a star is an indication that it is not stationary, but instead it is going around in circles. This kind of a motion of a star, because of an unseen companion. Okay, we have not seen the star, so we have not seen the planet. Our observation is on the star, and that's what we are using to infer the presence of a planet. So this kind of a motion of a star, because of a companion around it, it's called wobble motion. Or sometimes it's also referred to as reflex motion. And it is this reflex motion that astronomers use to infer the properties of the planet around the star. So just to lay down whatever I have just said, back and forth shift in wavelength in a star spectrum, that is what astronomers try to measure. And just to give you an idea of how small this shift is, okay, the wobble motion or the wobble velocity or the reflex velocity on a sun-like star, because of the presence of a Jupiter-like planet around it, is of the order of 12 to 13 meters per second. The reflex velocity induced on a sun-like star because of a planet like Earth revolving around it is of the order of centimeters per second. Okay, so this is these numbers are extremely small. You have to imagine that these stars are at light years of distance from us, and sitting here on Earth, by collecting their light and looking at the spectrum of that the star, we are trying to measure shifts in spectral lines produced by the star's wobble motion, which has velocities of the order of 13 meters per second, and for small planets of the order of 10 centimeters per second. A huge star moving with 13 meters per second or a few centimeters per second, that's a very, very tiny measurement to be made. And this is the reason why it took astronomers a very long time to actually discover the first extrasolar planet around other stars. This reason is because in order to do this, you need spectrographs with extremely good spectral resolution and excellent wavelength calibration. In other words, you need very high quality instrumentation to do that. So the optical engineering part is highly complex, and that it took years to come up with the kind of design and the kind of exact measurements that are required to make these fine spectral line shift measurements. Okay, so the entire thing is called high precision radial velocity measurements. I'll show you some pictures, one or two pictures of what a telescope looks like and what a spectrograph that is used for detecting exoplanets using radial velocity method looks like. So this is a telescope in the southern hemisphere. This telescope is owned by the European Southern Observatory, and this is the outside dome structure. If you go inside the dome structure, you can see the telescope. The telescope looks something like this. As you can see, it's a heavy piece of machinery. It's not like the small telescopes that we see in planetariums and science museums. The telescopes that are used for research purposes are huge equipments. And the purpose of the telescope is to collect the light. Okay? And this light that is collected is then sent to a spectrograph, which is usually kept in another room because the spectrograph has to be extremely stable to be able to measure these small shift in wavelengths produced by meter per second or centimeter per second movement of stars, which are light years of distance away from us. Okay, so these spectrographs are kept in a separate room, and the light from the telescope is taken to that spectrograph with the help of optical fibers. Okay. So here is a picture of a spectrograph that is exclusively used for discovering extrasolar planets around other stars, using radial velocity method. It's called HARPS, this particular spectrograph. HARPS stands for High Accuracy Radial Velocity Planet Searcher. And what you are seeing is the cylindrical enclosing of that spectrograph. Inside the cylindrical enclosing are the optical elements of that spectrograph. This cylindrical enclosing is there because once the telescope is ready for observations, what they do is they take all the air out of the cylindrical chamber through a vacuum pump system. And the reason why they take all the air out is because even movement of air along the path of the light beam can affect the measurements. Okay, so if air is passing through the path of the light beam, then as air moves, the refractive index will change, and that can refract the light that is coming to the spectrograph. So to avoid those kind of, so it's like fine tuning. What I'm trying to say is that this requires a lot of engineering work, and if you open this cylindrical chamber, you can see that it's a complicated design inside. Okay, so this is the inside of that spectrograph. So people who are working in the field of optics, optical engineering, people who are working in the field of control systems, people who are working in electronics, okay, microelectronics, etc. All those people, their contributions are vital in all fields of science, also astronomy, okay, because every discovery in astronomy is made possible because of some fine engineering work. So here is one example of that. So let's go a little bit more into this radial velocity method. I'm assuming that most of you who are listening to this are students of engineering and sciences. So that's why I'm going a bit, and I hope there are not many very young school students. Okay, so I'm just going a little bit into the theoretical aspects of this. So let's see how the shift in wavelength or the shift in position of the star relative to the center of mass, how that can be used to infer the properties of the extrasolar planet, which we have not seen. Okay. So here is a picture, a schematic diagram. The plus shows the center of mass of a star-planet system, and this red circle is the orbit of a star. So this orange thing is a star. I have not drawn the planet here because in radial velocity method, we don't get to see the planet, we only get to see the star. And what is shown here is an observer. So this is we are looking at this scenario from top. The orbit is along the line of sight of the observer. Okay. So we are looking from top, but the observer who is measuring the spectrum of that star is looking at it such that the orbit is along the line of sight of the observer. So when the star is here, okay, it is rotating around the center of mass. There we can draw its velocity vector like this. The velocity vector would be tangential to that point, and you can see that the entire velocity is pointing towards the observer. Okay, so that will cause a shift in spectral line. In this case, it will cause a blue shift because the velocity vector is pointing towards the observer. After some time, when the star has reached this particular position in its orbit around the center of mass, the velocity vector will be pointing like this. At this time, the entire velocity is perpendicular to the line of sight. Okay? There is no radial component. Only if there is a radial component of velocity, there will be a shift in spectral line. So at this point, there will not be any shift in spectral lines. Okay? So there is no velocity to measure. After some time, the star reaches here. The entire velocity is pointing away from the observer. So there will be a red shift. So again, we will see a shift. And when the star reaches this point, the velocity vector is perpendicular to the line of sight of the observer, so no shift is observed. Okay? So that means that if you are constantly monitoring the spectrum of a star, we will see blue shift, no shift, red shift, no shift, blue shift, like that. It's a cyclical pattern. And so if you take the velocity vector at any random point, and if you assign, if this dotted line is the radial component, and if you define an angle theta with respect to the radial component, then what we would be measuring is V star cos theta. Okay? So what that means is, if the star is going around in circles, it's like uniform circular motion with a constant velocity V star, then what we would be measuring would be V star cos theta, and this theta keeps changing with time. So which means the radial velocity that we measure, VR, which is the left-hand side of that equation, it changes like a cosine or a sine function. Okay? It will change like this. Okay? So if you are constantly monitoring the spectrum of a star, and if that star has a planet revolving around it, and if that star is exhibiting this wobble motion, then this is what we would see as a function of time. So this radial velocity curve, this is called the radial velocity curve. This radial velocity curve is the beginning or the most important measurement that is made in this technique for finding extrasolar planets. So I'll just go a little bit more from here, give you a glimpse of the theory behind it. So this is that same diagram which I drew earlier. Okay, the red is the orbit of the star around the center of mass. Now I am also drawing the orbit of the planet. Okay, remember that in radial velocity we cannot see the planet, but just for the sake of understanding, I've just drawn the planet's orbit. So the planet will be on the opposite side of the star relative to the center of mass. And so if A star is the distance of the star from the center of mass and AP is the distance of the planet from the center of mass, then VR is equal to V star cos theta, and so VR can be written as 2 pi A star by P cos theta, where 2 pi A star is the circumference of this star's orbit around the center of mass, and P is the time it takes for the star to go once around the center of mass. So 2 pi A star by P is nothing but velocity is equal to the distance traveled divided by the time taken for covering that distance. Okay, so that's what 2 pi A star by P is. So now if you look at the radial velocity curve, Vr is equal to some constant into cos theta. That constant is the semi-amplitude of this radial velocity curve. So if you measure the semi-amplitude of the radial velocity curve, we will get what is 2 pi A star by P. Okay? And P we can determine because P corresponds to one full cycle of this radial velocity curve. Going from 0 degree to 360 degree, one full cycle of this cosine curve will be the time period, because theta varying from 0 to 360 means the star has gone once around the center of mass. Now, interestingly, if you go back to this picture, you can see that if the star and the planet are in a dynamically stable system, if they form a dynamically stable system, then the time it takes for the star to go once around the center of mass will be the same time that it takes for the planet to complete once around the center of mass, one orbit around the center of mass. So only if that condition is satisfied will the planet and star remain on opposite sides of the center of mass. Okay? So the star and the planet's period around the center of mass is the same, so that period we get from the radial velocity curve. So if you substitute that in this above thing, then you will get what A star is. Okay? This can be used to find what is determine A star. In other words, how far away the star is from the center of mass. But we are interested in knowing more things about the exoplanet. Okay? We are not so interested in the star's orbit. We are using the star's orbit as a means to get to the properties of the planet. So let's see how we can do that. Okay, let's say that the mass of the star is m star and the mass of the planet is mp. Then Kepler's third law, I'm sure all of you remember this from your class 11 or 12. Square of the period is proportional to cube of the orbital separation between the star and the planet. Okay, so p square is equal to 4 pi square divided by g m star into 8 cube. That is Kepler's third law, where A is equal to the combined separation, the instantaneous separation between the star and the planet. In the case of circular orbits, A is a constant, okay, A star plus AP. And we can also write the expression for center of mass, which is m star A star is equal to MP AP. Now, as I already mentioned, A star can be determined from the radial velocity curve. Okay. From Kepler's third law, if you know the mass of the star, which is a quantity that can be estimated from the spectrum of the star itself. When we record the spectrum of the star, based on the spectrum, we can estimate what is m star, the mass of the star. Period we get from the radial velocity curve. So P is known, m star can be estimated, which means A can be determined from Kepler's third law. Once you know A star is already known, which means we can find what AP is, the orbital separation of the planet from the center of mass. Then we come to this expression, m star A star is equal to MP AP. M star we know, A star we know, AP also we know, which means that we can estimate the mass of the planet from that. Okay. So even without observing the planet, even without actually directly seeing the planet, by observing the star and its wobble motion, and by monitoring that wobble motion for sufficiently long period of time, we can, using simple laws of physics, we can determine a number of properties of the planet. For example, we can find out what is the mass of the planet, the unseen planet. We can find out how far away the planet is from the star. We can find out how long it takes for the planet to complete one orbit around the star. Okay? So we can infer whether the planet is like Earth or whether the planet is like Jupiter, very massive. we can infer whether the planet takes 365 days like the Earth to go once around the star, or whether it takes 80 days, 88 days like Mercury, or does it take several years like some of the planets of the outer solar system. Okay. And we can also find out how far away the planet is from the star. If the planet is very close, then the temperatures are going to be very high. And if the planet is very far away, then the temperatures are going to be very low. All these are parameters that are important if you want to speculate on the possible habitability of that planet, whether that planet could be supporting life or not. Okay, so I'm just going to skip this. There's too much of detail going into it. I don't know how many of you are interested. So I'll just do all that. Skip. So this technique, radial velocity method, has an observational bias. Okay? And what I mean by that is, if you do a survey of many stars in our own galaxy, many stars that we see in the night sky, if you do a survey of all those stars, collecting light from it and getting the spectrum of it and trying to see which stars are exhibiting this wobble motion, then you are likely to find many exoplanets through this radial velocity method. But if you look at the data for those exoplanets, you are likely to find that most of the planets are very massive, and most of those planets which are very massive, they are also orbiting very close to the star. And this is an observational bias, because the technique radial velocity method, in that technique, it's easy to find big planets orbiting very close to their star, because the gravitational force will be large and the wobbling, okay, the reflex motion velocity will be large. If the reflex motion is large, then it will produce a significant shift in spectral line, which is easy to measure compared to a tiny shift in spectral lines. So therefore, the radial velocity method, the data is skewed. If you look at it, there is a bias to it. So that's what this animation is trying to show. If you have a small planet orbiting around a star, the center of mass will be inside the star. The wobble will be very, very small. But if the planet is very large and if it's very close to the star, then the wobble motion is going to be bigger, and it will be easier to measure that. So when astronomers started detecting extrasolar planets using radial velocity method, after several years of discovery, they found out that most of the exoplanets that they were discovering, they were very massive planets. Planets with masses comparable to the mass of Jupiter, Saturn, etc. Sometimes much bigger than that, orbiting very close to the star. Okay? So that brings us presentation. Just skipping these slides, I don't want to. That brings this presentation to the first discovery of exoplanet. In the year 1995, a team of Swiss astronomers who were doing an observational survey, like what I just mentioned, trying to record the spectrum of those stars and trying to find this wobble motion, they found out that a particular star called 51 Pegasi, which is it's not a very bright star, but it's not too faint either. The star is very similar to the sun, 51 Pegasi. It lies in the direction of the constellation Pegasus. This star was exhibiting this wobble motion. And when they analyzed this wobble motion, they found out that this wobble motion can be best explained by the presence of an unseen planet around it. That planet was called 51 Pegasi b, and that was the first discovery of an extrasolar planet around a star like the sun. This discovery was made, so here is the radial velocity curve for that 51 Pegasi b. So what is shown along the y-axis is the reflex motion velocity, okay, or the radial velocity in units of meters per second, and along the x-axis is time period normalized to the orbital period. Okay. And each of the black dots that you're seeing, those are all spectroscopic measurements of the star 51 Pegasi. And when they tried to fit it with the Keplerian model, they found out the parameters. So they found out that the planet takes 4 days to go once around the star. Okay? And it was going around the star in a nearly circular orbit. The eccentricity was 1%, which means that it's almost a circle. Eccentricity of 0 means it's a circle, and larger eccentricities means it's like an ellipse. So here eccentricity is very close to 0, which means that the planet is in a nearly circular orbit, and the mass of the planet was estimated to be roughly half the mass of Jupiter. So this was the first extrasolar planet that was found. The planet was called 51 Pegasi b. The interesting thing, so this discovery was very, very interesting because here is a planet that is half the mass of Jupiter, which means that it is possibly a gaseous planet, big gaseous planet, which takes only 4 days to go once around the star. So Mercury, which is the planet that is closest to the sun in our solar system, takes 88 days, 88 Earth days to go once around the sun. 51 Pegasi b takes only 4 days, which means less than a week by Earth time standards. That means that this planet is incredibly close to the star. It's probably almost touching the surface of the star. So the first discovery itself threw up a lot of questions. For example, how can planets form so close to a star? The conventional theory of planet formation says that planets can form only far away from star where conditions are much more not so violent. Okay, close to a star, you have very high temperatures, strong stellar winds, strong influx of radiation, etc., which is trying to push things away. So how did such a massive planet form so close to a star? We don't have any such example in our solar system. So this led to the idea of planet migration, okay, which is an idea that's been explored in great detail by planetary scientists. So the idea is that this particular planet, which astronomers detected, it probably formed very far away from the planet. But over time, but it's not in a dynamically stable orbit. So what that means is over time, the orbit is decaying. The orbit is unstable. So the orbit is decaying and the planet is slowly spiraling in. And finally, it is going to go and plunge into the star. So we have observed the star when the planet is ridiculously close to the star. Okay? So anytime in the near future, the planet may go and plunge into the star. So this is called planet migration. Many planets that form around stars can be in unstable orbit. So what that means is that when we look at the present solar system, we see these 8 planets and some minor bodies also in the solar system. Most of them are in very stable orbits. At least the planets are in very stable orbit. But in the distant past, in the early phases of the solar system, the early years of the solar system, our solar system probably had many more planets than the 8 planets that we see today. Not all of them were in dynamically stable orbits. There were planets which probably were in highly unstable orbits, and either they plunged into the sun over time or they got thrown out of the solar system because of some gravitational kick from the sun. So some kind of a trigger or some kind of a perturbation from the sun. So this with the help of computer simulations, astronomers are now studying planetary formation with this kind of scenarios modeling in. Okay. So the discovery of the first extrasolar planet, 51 Pegasi b, around a sun-like star, okay, was made by these 2 people. On the right-hand side is Michel Mayor, and the left-hand side is Didier Queloz. Both are Swiss astronomers. So they made, and behind the backdrop is the telescope which they used to make this discovery. And this discovery happened in 1995. So if you are less than 25 years old, then this discovery happened before you were born. And for the discovery of the first planet beyond the confines of the solar system, beyond the boundaries of the solar system, for this discovery in 2019, Michel Mayor and Didier Queloz were awarded the Nobel Prize in Physics, okay, 25 years later. So this is the paper which they wrote in Nature magazine announcing to the world the discovery of this extrasolar planet. Okay. So after 1995, in the years that came by, many exoplanets were discovered, and each one was very different from the planets of the solar system. So for example, here is another example. Around a star called 16 Cygni, they found that there is a planet that is roughly twice the mass of Jupiter, and it goes around the star with a time period of about 800 days. Okay, so that means more than twice the time it takes for Earth to go once around the sun. So this is a long period planet. So planet came in lot of variety. Okay, and this radial velocity method since then has been extremely successful in helping astronomers find extrasolar planets around stars. So now we come to the second method, transit method. I'll try to go quickly so that I don't take up too much of your time. Okay, so transit method, in radial velocity method, we were measuring the wobble motion. In transit method, what astronomers do is they constantly monitor the brightnesses of stars. Okay. And the idea is that suppose we are constantly monitoring the brightness of a star, and as we are monitoring the brightness, if a planet happens to move in front of that star, okay, so this planet is going around that star. So when we are looking at it and constantly monitoring its brightness, during that time, if a planet happens to move in front of that star, then for the duration of transit, for the duration for which the planet moves in front of the star, that's what called transit. For the duration of that transit, the brightness of the star will dim a little bit. That is because the planet is blocking the starlight. Okay. And since planets are much smaller compared to stars, the planet is not going to completely block the starlight. It's only going to block a tiny region of the star, which means there is going to be a slight reduction in the brightness of the star. And once the planet moves out of the way, once the transit is complete, the star's brightness comes back to its normal value. Okay. And the next time, when the planet again completes one orbit around the star, and next time it passes in front of the star with respect to us, okay, as we are observing, then again there will be a dip in brightness. So this periodic dip in the brightness of a star can be used to infer the presence of a planet around it. And let me just remind you that this is an animation. Okay, this is just a visualization. Transit method is also an indirect method, which means that we don't get to see the planet. In just like radial velocity method, in transit method also, our observation is on the star, and by constantly monitoring the brightness of the star, we are and by seeing a dip in the brightness, we come to this conclusion that there is a planet around it. Okay? And this is a very fine measurement. Even though I am saying it in very loose terms, I don't think that this is a very shoddy kind of affair. Okay, this is done to great precision. Okay? I'm just giving you an overview of it. So if there are multiple planets around a star, for example, if there is a small planet and if there is a big planet, then what happens is when the small planet transits in front of the star, you will see a small dip in brightness. And when the big planet transits in front of the star, we will see a big dip in brightness. So the depth of the dip in brightness is an indication of how big a planet it is. Okay. The more mass, the bigger the planet, the more will be the dip in brightness. That's what this animation is trying to show. Now it depends, the dip in brightness not only depends on the size of the planet, it also depends on the size of the star. So in reality, what it depends on is the relative size between the planet and the star. So for example, here is a small star, and if a planet is passing in front of that star, we see that the brightness dips by a certain amount. But if that same planet were going around a bigger star, okay, then the dip in brightness will be smaller, because compared to the total light that we are getting from the star, only a small part is blocked out. Okay. So in other words, if you are constantly monitoring the brightness of a star, okay, that's what this diagram is showing. Along the y-axis is the brightness of a star, and along the x-axis is time. Okay. The brightness remains a constant for most part, but when a planet transit happens, the brightness dips down. And then when the planet moves out of the way, the brightness again comes back to its normal value. And then again, when the planet transits, it dips down. Okay. The depth of this dip is going to be proportional to the ratio of the size of the planet to the star's size. So if you can calculate, or if you can estimate what is the star's radius, then we can find out what is the size of the planet, which we have not seen. So radial velocity method gave us the mass of the planet. Transit method gives us the size of the planet. Not just the size, it also gives us how long it takes for the planet to complete one full revolution around the star. That is given by the separation between the dips in brightness. So if there are multiple planets, what happens is you will see multiple dips, and each dip will have a different magnitude. Bigger planets transiting in front of the star will produce bigger dips. Smaller planets transiting in front of the star will produce smaller dips. And the separation between those dips will also be different, because each planet has a certain time period. So all that information can be obtained by constantly monitoring the brightness. And this is the essence of transit method. Okay. And using transit method in 1999, okay, so that means 4 years after the first extrasolar planet was discovered using radial velocity method. In 1999, astronomers discovered the first planet, exoplanet, using transit method. This was discovered around a star called HD 209458, and the planet is called HD 209458b. So these are catalog numbers, you don't have to worry about it. So what you are showing, what you are seeing here is real data, and the y-axis is the light, amount of light that we receive from the star, and x-axis is time, and you can see that the light is a constant, and then suddenly it dips, and then it again recovers. The important thing to note here is, if you look at the values on the y-axis, you can see that when there is no transit happening, the value is 100. And when the transit is happening, the value dips down to 98.5, which means that the dip in brightness is of a value of 2.5% of the star's brightness. So it's not like the star is going to drastically dim in brightness. When a planet transit happens, we are making a very fine measurement. The star's brightness dims by a few percentage, that's all. Which means that it requires, once again, very careful observations, very precise instrumentation, etc. Okay, transit method. So using transit method, many exoplanets have been discovered. I just want to show you one such example. So TRAPPIST-1 is a star, and around the star TRAPPIST-1, astronomers discovered 7 extrasolar planets around one star, 7 exoplanets using transit method. And the dip in the brightness of the star TRAPPIST-1, because of these 7 planets transiting in front of that star at different time periods, is what is shown in this graph here. What is interesting here is, if you look at the time periods of these planets, okay, one planet takes about 1.5 Earth days to go once around the star. Another planet takes about 2.5 Earth days. The third planet takes about 4 Earth days. The fourth one takes about 6 Earth days. The fifth, 9 Earth days. The planet that takes the longest period takes only about 2 weeks to 3 weeks of time. Okay, whereas we take 365 days, okay, to go once around the sun. So which means that all these planets, these 7 planets revolving around TRAPPIST-1, they are all orbiting very close to the star. So here is an entire planetary system of not one planet, but 7 and probably more, many more also. And they are all orbiting the star at very close by distances, taking only a few days to go once around the star. And this TRAPPIST-1 is not a very big star. It's a very, very small star, much smaller and much cooler than the sun. So if you were to compare the TRAPPIST-1 system with our solar system, the entire TRAPPIST-1 system with the star and all the 7 planets can be fitted well inside the orbit of Mercury. Okay, so this is completely unlike what our solar system is. Okay, so this is what is happening in the field of extrasolar planet studies. Every exoplanetary system that astronomers are finding is telling us how diverse planets can be in this universe. So the properties of extrasolar planets that can be established from transit method is the size of the planets, its orbital time period, etc. Now both these methods, transit method and radial velocity method, as I mentioned, are indirect methods. We don't get to see the planet. Okay, we can only infer the presence of a planet. What will be really exciting is to be able to see the planet. Okay, so that is the real excitement. If you can actually see a picture of the extrasolar planet, then there's nothing as convincing as that. But in the beginning of the presentation, I told you that there are some great barriers. There are some challenges in directly photographing extrasolar planet, directly taking pictures of exoplanets. In the last 10 to 15 years, because of some significant improvements in optical engineering, particularly the invention of adaptive optics, okay, astronomers have been able to do very high contrast imaging of stars, and with some other image processing techniques also, they have been able to take pictures of extrasolar planets. Okay, so here is one example. HR 8799 is a star that is about 130 light years of distance from us. That means that light takes 130 years to reach us from that star. And using high contrast imaging, using this Keck telescope and Gemini telescopes, which are fitted with adaptive optic systems, which is what AO represents, they were able to see 4 planets around the star. So in this picture, the center portion is the star, and the light from that star has been removed, has been subtracted out. If the starlight is present there, then what happens is it will the light will be spread around that star, and we will not be able to see the planets around it. So the starlight is subtracted out so that you get better contrast. And what is labeled here as B, C, D, and E, these are 4 planets that are revolving around HR 8799. And all these planets are revolving around the star at very large distance. Okay, and people have been monitoring, astronomers have been monitoring this HR 8799 system for a very long time. So what I'm going to show you next is an animation. This is real data. Okay, this is not computer simulation. This is real data. By constantly monitoring this HR 8799 system for 7 years, astronomers have put together this GIF animation. In the center black region, that is where the star is, and the starlight has been blocked. Okay, it has been subtracted out. You can see 4 bright objects around it. One at the top left corner, that is B, C, D, E, the 4 extrasolar planets around the star HR 8799. And I'll play the animation, and you can see at the bottom the dates changing. And as the dates change, you can see that the planets are also moving around the star. So that is 7 years of data put together, 4 seconds of animation. So this shows that these planets are actually revolving around that star. Okay? So what you are looking at here are actual images of extrasolar planets. So if there were alien astronomers, if there were aliens in some of these distant stars, and if there are astronomers in those distant planets, and if they take a direct image of our own solar system, they are probably going to see something like this. Okay, all the big planets like Jupiter, Saturn, Uranus, etc., going around the sun in a similar manner. This does not mean that these are the only 4 planets in that planetary system. There are probably many more planets that's much closer by orbits, but it's very difficult to see them because of the light from the star. So here is one more example. Beta Pictoris is a nearby star. It's not very far away from us. And around Beta Pictoris, astronomers have found the existence of a single planet. Okay, there are probably many more planets, but at least one planet has been found. And the star is this black circle, and the planet is the bright object that is moving. So I just want to end the presentation by showing you this histogram. Okay, so prior to 1995, the only planetary system that we knew of was our own solar system. And in the last 30 years or so, the number of extrasolar planets has swelled in numbers. The extrasolar planets that we know of has increased in numbers by several hundreds to thousands. Today, as of date, we know of the existence of more than 4,000 extrasolar planets orbiting around various stars. Okay. And that all that has happened in the last 3 decades. So this is a histogram that shows the number of extrasolar planets that were known in each year. So you can see that before 1995, the histogram is almost 0. And after 1995, the histogram is slowly growing. It's a cumulative histogram, which means whatever data point is in one histogram, it is added to the next one. The color coding represents the different techniques that were used to find those extrasolar planets. So red means those planets were found using radial velocity method. Green means they were found using transit method. And as you can see, the graph initially is dominated by red, which means that in the early years, most of the extrasolar planets were found using radial velocity method. But in the last 10 to 15 years, the transit method has been tremendously successful in finding extrasolar planets. It's been so successful that if you take the total number of extrasolar planets that we know today, which is around 4,300, 70% of it has been found through transit method, and about 25% through radial velocity method, and the remaining 5% through all the other methods. And the reason why transit method has been so successful is because in 2009, the American Space Agency launched a telescope into space. The telescope is called the Kepler Space Telescope, and Kepler Space Telescope was launched with an exclusive mission to find planets orbiting other stars using transit method. So this Kepler Space Telescope, it is no longer operational. Okay, it completed about 10 years of operation in space, from space. And during that 10-year operation, it kept on monitoring the brightness of about 150,000 stars in a particular region of the sky. And it found about 2,600 extrasolar planets orbiting many of those 150,000 stars. So Kepler really revolutionized the field of exoplanet studies. It almost doubled the number of, Kepler helped astronomers to double the number of extrasolar planets that were known. So just to give you an idea on how important and how successful Kepler Space Telescope has been. So here is a graph that shows the number of extrasolar planets that were known before Kepler Space Telescope mission. Okay. So along the y-axis is the mass of the planet, and along the x-axis is orbital time period. The line, the dashed line at 1 corresponds to 1 Earth mass. The dashed line above that corresponds to the mass of Neptune, and the line above that corresponds to the mass of Jupiter. Okay, so any planet above that line is more massive than Jupiter. Any planet above the Earth line is more massive than Earth, etc. And you can see that this is how the graph looked before Kepler Space Telescope. After Kepler Space Telescope, this is how the graph looks. All the yellow data points that you're seeing on the right side panel, those are all data points added to this plot by the single mission, which is the Kepler mission. And you can see that Kepler has really populated this graph by discovering thousands of planets around other stars. And what is of most interest to us is the number of planets with mass similar to that of Earth and mass smaller than that of Earth, which means that these are all likely to be rocky planets, terrestrial planets. And possibly many of them have a dense atmosphere, and probably some of them support liquid water. In other words, probably many of them have conditions that are conducive for the existence of life. Okay. So Kepler mission was decommissioned in 2018, but after Kepler, there are several other missions that are planned, which are going to make a lot more discoveries in this field of exoplanet studies. TESS is a mission that is already up there in the sky. It has already launched, and TESS data is just coming through. And TESS is expected to make many more discoveries than what Kepler did. So this is going to be a very active field of research, and there are going to be many interesting discoveries coming out in the future. Okay, so I just want to conclude this presentation by saying that, even if you forget all the details that were discussed in this presentation, the final takeaway message is, in the last 25 to 30 years, the research in extrasolar planet studies have shown us that there are probably more planets in our galaxy than the number of stars that are there in our galaxy. Or probably there are more planets in our universe than the number of stars in our universe. Okay. So when we look at the night sky, we see all these twinkling stars, this countless number of stars in the sky. So what you have to imagine in your head is, each of those stars are likely to have several planets revolving around them, just like planets are going around the sun. It's just a matter of finding them. So in fact, the research on extrasolar planet studies has convinced astronomers that statistically that planet formation is a natural outcome of star formation. Whenever stars form, planets also form around it. So if planets are so common, okay, if they are more common than stars in our universe, then that really increases the odds of finding a planet that is similar to Earth in many respects. Okay, for example, a planet that is at the right distance from the star, where water can exist in liquid form, a planet with a dense atmosphere that can keep the heat trapped inside the planet so that conditions are favorable for higher life forms to evolve. Okay, so these are called habitable worlds. So I'm not saying that astronomers have found habitable planets around other stars, but this is the first crucial, finding those planets is the first crucial step. There are many interesting things that are happening at the frontiers of these research fields. For example, now astronomers are detecting atmospheres of these extrasolar planets. So going from detecting those planets, now astronomers are able to find what is the chemical composition of the atmospheres of those planets. The reason why this is important is because there are certain elements, if they are present in abundance in a planet's atmosphere, then that is an indication that the planet has life in it. For example, if you look at Mars, Earth, and Venus, these are 3 planets which are roughly at the same distance from the sun. Mars and Venus has an atmosphere that has a lot of CO2, carbon dioxide, and very little oxygen, molecular oxygen or water vapor or ozone. Whereas Earth has a lot of water vapor and O2, molecular oxygen and ozone, O3 in its atmosphere, and its amount of CO2 is much less. So we know that the reason why Earth has such an oxygen-rich atmosphere is because of photosynthesis that happens on Earth. With the emergence of life on Earth, with the emergence of photosynthetic algae roughly 2 billion to 3 billion years ago, that is when the Earth's atmosphere became oxygen-rich. So the detection of oxygen in an exoplanet atmosphere can be an indication that the planet has a biomass. Okay? So for this reason, astronomers are now trying to find atmospheres of these exoplanets. But we are far from answering this question of whether we are alone in this universe or not. Okay, we don't know whether the phenomenon of life exists anywhere else in the universe. People are still searching. So let me just end this presentation by this famous quote from Arthur C. Clarke, that there are two possibilities: either we are alone in this vast cosmos or we are not. Both are equally interesting and exciting possibilities. So with that, let me just end the presentation, and I'll be happy to answer questions.
Hello, sir.
Yeah.
Sir, you have told that now we can just measure the properties. We can look into the properties of the atmospheres of these exoplanets. So
Right.
without reaching there, how are we going to do so? What is the way we are doing so? How do we do?
So the way, correct. So the technique that is used to detect the atmospheres of these exoplanets is the following. Okay. So if you have a planet that is going around a star, when the planet is transiting in front of that star, the light from the star will pass through the atmosphere of the planet. Okay, so when we collect that light and when we record its spectrum, okay, we will see absorption features, absorption lines produced by molecules that are present on the surface, on the atmosphere of that planet. So if you see absorption line from molecular oxygen or water vapor or CO2 or methane or something, then that is an indication that it is coming from the atmosphere of that planet. Because when the planet moves out of its way, when the transit is complete, when you record the spectrum of that star, you will not see those lines. Again, when the transit is happening, if you record the spectrum of the star, you will see those absorption lines coming into the spectrum. So some absorption lines will come into the spectrum only when transit is happening, and they will go away when the transit is over. So that means that these absorption lines are coming from the atmosphere of the planet through which the light of the star is passing through. Okay, that is one method. The other method is I showed actual pictures of extrasolar planets. That means like direct imaging, HR 8799 and Beta Pictoris, etc. So that means that we are getting photons from those planets. That's why we are able to take pictures of them. So one can actually take those photons and record a spectrum, which means we can directly get the spectrum of the planet itself without relying on the star. Okay, so that is another way of finding out what kind of an atmosphere the planet has. So this one is called transmission spectroscopy, the other is called direct thermal emission spectroscopy. So these are the ways by which people are trying to characterize the exoplanet atmospheres.
Thank you so much, sir. It was really awesome listening to you.
Thank you. So there is a question in the chat box from Navaneet. He's asking, wouldn't it be difficult to find planets using these methods, as most of the star systems are being redshifted due to the expansion of the universe? Okay. So what he's saying is that the stars are all receding away from us because we are living in an expanding universe. So wouldn't it be difficult? Okay, so let me just clarify something there. The fact that we are living in an expanding universe is only true when we are looking at distant galaxies. As far as stars that we see in the night sky are concerned, all the stars that we see in the night sky with our unaided eye and with the help of telescopes, they are all stars that belong to our own galaxy, the Milky Way. Okay. It's very difficult to see individual stars in faraway galaxies because of the large distances. In the case of galaxies, it's millions of light years to billions of light years. So it's very difficult to see individual stars. So the stars that we see in the night sky are all stars in our own galaxy. And all these stars are held together by the gravitational potential of our galaxy, which means they are not expanding with the expansion of the universe. Just like, if you are living in an expanding universe, you may ask, if the universe is expanding, then why is the distance between the planets of the solar system not increasing? The reason is because the planets of the solar system are held together by the mutual force of gravity between the sun and the planets. In the same way, all the stars in the Milky Way are held together by the mutual gravitational force of the Milky Way. Okay? Or the more correct statement is by the gravitational potential of the Milky Way. So those stars are not participating in the expansion of the universe. Only when we look at faraway galaxies, we will find that those faraway galaxies are moving away from us, which is an evidence that we are living in an expanding universe. So Navneet, to answer your question, this expansion of the universe doesn't come into picture when we are monitoring the spectra of stars within our own galaxy. Any other question? Okay, so Abhishek Shaju is asking, in midst of all these space telescopes, what is the output that we can expect from satellites such as AstroSat? So for those of you who are not familiar, AstroSat is India's first indigenous exclusive space telescope. That is what AstroSat is. AstroSat has been extremely successful in making many discoveries, but not in the field of exoplanet studies. Kepler Space Telescope was a telescope that was designed exclusively for the purpose of finding planets around other stars using transit method. The purpose of AstroSat, meaning the purpose of the payloads on AstroSat, is to study the universe at high energies. Okay, so it is to look at galaxies at ultraviolet wavelengths, at X-ray wavelengths. It is to look at active galaxies, AGNs or quasars in all those wavelengths. It is to look at some stellar remnants like white dwarfs, neutron stars, etc. at those high energies. So the purpose of AstroSat was primarily to study our universe at high electromagnetic radiation energies. So it is not built, it was not designed for the purpose of exoplanet studies. But having said that, let me also tell you that Indian Space Research Organization, Department of Space, is seriously considering proposals for putting a telescope in space to find exoplanets. So this is going to be India's own space observatory for finding exoplanets. But as you may know, our space agency is a much younger space agency compared to the European and American space agencies. First of all, European Space Agency is a consortium of space agencies of half a dozen or a dozen countries. Okay, so Germany, France, Italy, all these countries put together is European Space Agency. US Space Agency is of US itself, and these are these are countries which have been investing in science and technology for a much longer period of time. If you look at Indian Space Research Organization's history, most of ISRO's history has been to build satellites, to launch satellites for the immediate benefit of humankind. Okay, so what that means is communication satellites, remote sensing satellites, etc., because that was the need of the nation when we reeled out of more than 200 years of foreign rule after independence. Okay. So there was a lot of need to lift the country both technologically and in many other areas. So for that reason, ISRO was focusing mostly on satellites that had immediate benefit to human society. Only in the last several years, ISRO has been venturing into fields like astrophysics, and there is a lot of support for astrophysics payloads, etc., from the Space Research Organization. So in the coming years, I think there are going to be many more. Okay. Are there any other questions? So Navneet is asking one more question. Sir, is it possible for life to only exist in Goldilocks zone? So there is a word that he has used, Goldilocks zone. So Goldilocks zone, I don't know how many of you are familiar with it. It's a poetic way of saying habitable zone. So astronomers have this definition of habitable zone, which is the distance from a star where water can exist in liquid form. And the reason why this definition is based on water is because the only example that we have of life is life on Earth. Okay, that's the only example that we have. And we know that most of the life forms on Earth are heavily dependent on the existence of water, on the availability of water. So life on Earth is based on the presence of water. Water is a prerequisite for life. So therefore, when we try to define life elsewhere in the universe, we have to define life based on the one example that we have here on Earth. So therefore, in the search for life elsewhere in the universe, astronomers also think of water as an important ingredient for the presence of life. Based on that, this habitable zone is defined. Okay? So habitable zone is the distance from a star where water can exist in liquid form. Which means if this planet is very close to the star, then the temperatures will be so high that it will be more than 100 degrees centigrade. All the water will boil off and it will be in vapor form. There won't be any liquid water. If the planet is too far away, then the temperatures will be too low. It will be less than 0 degrees centigrade, which means that all the water, whatever water is present, will be in the form of ice. Neither of which is the form in which we want water for life to arise, for life to thrive. So there is a sweet spot, there is a sweet zone around any star where the temperature is between 0 degrees centigrade and 100 degrees centigrade. That's called the habitable zone. It's also referred to as the Goldilocks zone, where it's neither too cold nor too hot, where the temperature is just right enough for water to exist in liquid form. So as of now, the speculation is that that is the place where life is likely to be present, if at all life is there. But as I mentioned, it's all based on the one example that we have of life, which is the life on Earth. Okay, possibly if life as a phenomenon can probably arise in other forms also, but I don't think there is any definitive answer to that. For example, we don't have a theory. We don't have a theory on how life originated on Earth. It is still an open question, how life originated on Earth. Whether life was seeded on Earth from outer space, this is one hypothesis that people have put forth. Okay, so there's a lot of uncertainties associated with that. Maybe one last question if anybody has a question. Otherwise, we can maybe wrap it up. So looks like there are no questions. So shall we stop? Avinash?
Yes, sir.
Okay, sir.
I'm quite excited, sir. Let's stop,
Yeah.
because some of the students are even asking questions or terms they are using, which even I am not familiar with. So that quite shows their excitement to the field or their interest to the field. So very happy. So I'm Avinash, and I'm student that comes to the IIIE of GEC Wayanad. So thank you so much for your time, sir. And one question I would like to ask is that since even there are exams going on, still a lot of participation we have seen in this. So can you speak a bit about the opportunities that engineering students have in astrophysics or in astronomical field?
Yeah, so it requires another lecture by itself. Okay, but I'll try to give a quick answer to that. So I don't know how many of you know this. So I did my BTech in Electrical and Electronics Engineering from College of Engineering Trivandrum. Okay, so after 12th, like everybody else, I also jumped into the engineering bandwagon. But I had a peripheral interest in physics. Okay, so I won't say that I was very good in physics, but among all the subjects which I studied in class 11 and 12, physics is the subject that I was attracted towards. So I started reading about astrophysics during my engineering years by myself, and then I realized that even if I have done an undergraduate degree in engineering, that won't prevent me from going for higher studies in astrophysics. So I think most of those who are listening this presentation there are also a lot of engineering students. So I just want to tell you that you don't have to have an MSc in physics to apply for a doctoral program in astrophysics. In fact, if you look at the national institutes that take students for PhD in astrophysics, and national institutes, what I mean is institutes in India of eminence, like the Inter-University Center for Astronomy and Astrophysics, or Tata Institute of Fundamental Research, or Raman Research Institute, or IISc. If you go to the Astrophysics department webpage, and if you look at the PhD eligibility, you will always find a statement that says that we strongly encourage students from BE, BTech, ME, MTech backgrounds to apply for our PhD program. So only thing is, you should, since academically engineering doesn't teach much physics, you have to find a way to teach yourself physics, because all these places are going to accept students for research in astrophysics based on a test that is done in physics, that tests your physics knowledge. So you have to, I mean, in this age of internet, I don't have to tell you how to do self-learning. There's ample resource available. There are many online courses available. So at your spare time, if you can teach yourself physics, then you can apply for any program, any astrophysics program in India or abroad also. That's one point. And the second point is, in terms of career opportunities, astrophysics being a fundamental research discipline, most of the career opportunities are restricted to academia, which means universities, research institutes, etc. So you're not going to get as many job opportunities like an MBA or a software engineer or something like that. But there are, every country is heavily investing in fundamental research in sciences. India is also opening its doors to basic research science. It has already started happening. Okay, there are many research institutes, and all these places are constantly looking for young people to join their workforce. So there is a lot of opportunity for people who do a PhD in astrophysics to get a job, a research/teaching job in astrophysics. So future definitely looks prosperous. If you pursue astrophysics, if you want to pursue astrophysics as a career, the only thing to keep in mind is, education-wise, it's a long innings. Okay, so after BTech you may get a job, but if you want to establish yourself as a researcher in astrophysics, you need to have a PhD, which means another 5 to 6 years of doing research, etc. So you have to be prepared for a slightly longer innings. Okay, but it's a fascinating field to get into. You get paid for thinking about fundamental questions about our own existence and the universe that we live in. So it's a great career. So anyone is welcome. That's what I want to share. Okay, it's probably not a wholesome answer, but you can go and look up online for opportunities, more opportunities.
Okay, sir. Thank you, sir.
Yeah. If there are no more questions, then can we?
Yes, sir.
Yes, sir. As we all know, it was a really good session today. So, on my behalf, I represent heartily thanks to Dr. Anand sir, who spared some time from his busy schedule. We were indeed grateful to have you, sir. I also thank Avinash sir for giving this opportunity, and also I thank each and every student who has joined us today. So, have a great day.
Thank you, and all the best to all of you. Thank you.
Thank you so much, sir.